Okay, today we are going to learn about the quantum numbers. Quantum numbers. In the Bohr model of atom, you learn that there is a nucleus in the center, a positively charged nucleus, and around this nucleus there are circular orbitals, and in these circular orbitals, electrons are revolving. Right? Electrons are revolving in the circular orbits. But in the quantum mechanical model of atom, the electrons are not revolving in circular orbits like this. The quantum mechanical model of atom is much different. Here, electrons can be seen around the nucleus in certain region. Okay, the electrons can be seen around the nucleus in certain region, and this region around the nucleus where there is a maximum probability to find the electron, and that region is called the orbital means the region around the nucleus where there is a maximum probability to find the electron, that's called orbital. You have learned about different type of orbitals: s orbital, p orbital, d orbital, f orbital, like that, right? So you know the shapes of different orbitals also. For example, you know that s orbital is spherical. Okay, actually it is a spherical cloud. S orbital can be treated like a cloud, spherical cloud, and that is a region around the nucleus, a spherical region around the nucleus, and in this region there is a very high probability to find the electron. Okay, so that is called an orbital. But p orbital is different from the s orbital. They are this type of dumbbell shaped orbitals. Okay, so there is a maximum probability to find the electron in this region around the nucleus. So these type of regions are designated as orbitals. Okay, orbitals. And this orbital, the concept of orbital is a product of the quantum mechanical model of atom. Quantum mechanical model of atom. These orbitals are designated by a set of numbers. Each orbital, like s orbital or p orbital or d orbital or f orbital, the orbitals in an atom are designated by a set of numbers, and these numbers are called quantum numbers. So quantum numbers actually are the address of orbital. Okay, we will come to the detail of that. Okay, the electrons are occupying the orbitals, therefore quantum numbers, maybe we can say that the address of the electron itself, right? Okay, and there are different quantum numbers, and some quantum number may be representing the energy, and some other quantum number represents the shape of the orbital, and some other quantum number may be there to determine or to say the orientation of the orbitals. Okay, so there are different quantum numbers to specify these different things. Okay, the first one, which specifies the energy of the orbital, is the principal quantum number. Principal quantum number. The second one, which deals about the energy, and that is azimuthal quantum number. Azimuthal quantum number. Azimuthal quantum number. This can be also called as angular momentum quantum number. Angular momentum quantum number. Okay, and the orientation is determined by the magnetic quantum number. Magnetic quantum number. Okay, so if these three quantum numbers are there, we can talk about an orbital, or we can get the address of an orbital. Okay, and we again know that each orbital is occupied by the electrons, and each orbital can have two electrons. Then we need another quantum number to represent this electron, and that is spin quantum number. Spin quantum number, and this applies to the electron which is inside the orbital, or electron occupying the orbital. Okay. So we are going to learn in detail of these four quantum numbers: principal quantum number, azimuthal quantum number or angular quantum number, magnetic quantum number, and spin quantum number. First of all, let us discuss about the principal quantum number. Principal quantum number. Principal quantum number. Okay. So the principal quantum number, as I already said, it determines the energy of an electron. It determines the energy of an electron. Energy of an electron. Okay. And this also determines the average distance of an electron from the nucleus. Average distance of an electron from the nucleus. Average distance of an electron from the nucleus. Okay, you have already familiarized with this quantum number, principal quantum number, if you have learned the Bohr atom model. If the principal quantum number can have the value, it is represented by the number n and by the letter n. N can have values 1, 2, 3, 4, etc. Okay, and if n is equal to 1, it represents the k shell. If n is equal to 2, then it represents the L shell, and if n is equal to 3, then it represents the M shell, and if n is equal to 4, it represents the N shell, etc. Okay, so n can have all these values 1, 2, 3, 4, etc. Actually, these are quantum mechanical consequences. Okay, these numbers. And in the Bohr model of atom, you have learned that the energy of an electron in the hydrogen is given by the hydrogen atom is given by En is equal to minus 2 pi square m e raised to 4 k square divided by n square h square. Here this n square, okay, in the here n represents the principal quantum number. So the energy depends upon the principal quantum number. Okay, this is the mass of the electron, this is charge of the electron, and k here actually is k is 1 divided by 4 pi epsilon 0. 1 divided by 4 pi epsilon 0. Okay, 1 divided by 4 pi epsilon 0. That is k. And so k is already known, and then h is the Planck's constant. Therefore, energy depends on the quantum number n. Okay, so from this equation we can know that n is in the n is in the denominator. So if the value of n increases from 1 to 2 to 3 like that, then what do you expect? En should decrease, but you have to consider that there is a negative side, though, therefore En actually should increase, right? So as n increases, the energy of the electron also increases. So the energy of the electron is determined by this principal quantum number. Okay, and now we can move on to the next quantum number, that is angular momentum quantum number or azimuthal quantum number. Angular momentum quantum number. Angular momentum quantum number or azimuthal quantum number. Azimuthal quantum number. Okay, and this quantum number is represented by the letter L. Okay, Principal quantum number is represented by the letter N. Here azimuthal quantum number is represented by the letter L. Okay. And this quantum number determines the angular momentum of the electron. It determines the angular momentum of the electron. Okay. And it also determines the shape of the orbital. It also determines the shape of the orbital in which the electron is located. Okay, so what are the possible values of L? L can have the values from 0 to n minus 1. So the values of L depends upon n. Okay, the L can have the values from 0, 1, 2, 3, etc. to n minus 1. So let us take, for example, the case where there is where the value of n is equal to 1. If n is equal to 1 means k shell, right? K shell. So in this shell, L can have the values L is equal to 0 to n minus 1, means 0 to n minus 1 in this case is 1 minus 1. So the minimum value is 0, maximum value is also 0. So L can have only one value, that is L is equal to 0. And if L is equal to 0, that corresponds to S orbital or S subshell. Okay, it corresponds to S subshell. S subshell. L is equal to 0. S subshell. So from here, from shell, we have reached it to subshell. Okay. Initially, we had in principal quantum number. From the principal quantum number, we have the shell, and from the shell, now we have reached the concept of subshell. Within the K shell, there is only one subshell, that is S subshell. Okay, means the first shell can have only one subshell, that is S subshell. And if n is equal to 2, n is equal to 2 means L shell, right? L shell. If n is equal to 2, then L can have the values, which is the minimum value 0, maximum value n minus 1. In this case, n minus 1 is 2 minus 1. So 2 minus 1 is 1. So L can have the values 0 and 1. Here L is equal to 0 represents again S subshell, and L is equal to 1 represents P subshell. Okay. And now we can go for the next one, that is n is equal to 3, that is M shell. And here L can have the values L is equal to the minimum value is 0, maximum value is n minus 1. N minus 1 in this case is 3 minus 1 means 2. Therefore, it can have the values 0, 1, 2. 0 represents S subshell, 1 represents PE subshell, and 2 represents D subshell. Okay. So within the third shell or M shell, there can be 3 subshells, S, P, and D. In the second shell, there are only 2 subshells, S and P. In the first shell, there is only one subshell, that is a S subshell. Okay, like that you can get the subshells within a shell. So from shell, we have reached a subshell. Now we can go for the next quantum number, that is the magnetic quantum number. Magnetic quantum. Okay, and this is represented by M. And this quantum number refers to different orientations of electron cloud in a particular shell, subshell. So this determines the orientation of electron cloud, means orientation of the orbitals within the subshell. Okay, so we can check what are the possible values of M. The possible values of M is equal to minus L through 0 to plus L. Okay, these are the possible values of M. So how many values are possible for M? 0 is possible, so there is one value. After 0 there are L values possible, right? And before 0 there are L values possible. So totally there are 2L plus 1 values possible. So maximum L values are, maximum M values are 2L plus 1 values. So we can check for different L values which are the possible M values. Let us take the example of L is equal to 0. That is a minimum value of L, and it corresponds to S subshell. S subshell, right? And corresponding to this, which are the M values? M is equal to minus L to plus L. It means minus 0 to plus 0. It means 0 only, right? So the only one possible value here is M is equal to 0. Only one possible value. And this corresponds to S orbital. S orbital. So from shell we reached a subshell, and from subshell we reached a orbital. Okay, and for L is equal to 1, it means that which subshell it is? P subshell. P subshell, right? For that, the possible values of M are minus 1 through 0 to plus 1, means minus 1, 0, plus 1. These are the possible values of M. Okay, so there are three values possible. Out of these three values possible means three orbitals are there. Which are these three orbitals? These are px, py, and pz orbitals. Okay, so these values corresponds to px, py, and pz orbitals. Actually, L is equal to 0 corresponds to the pz orbital, and it is not correct to say that L is equal to minus 1 represent px and L is equal to plus 1 represent py. That is not correct to say that actually. Actually, both of these, okay, minus 1 and plus 1, both belong to px and py. You may not understand that now, because we will be taking the combinations of this one to generate two orbitals, okay, and that you can learn when you are learning quantum mechanics in deep. I just wanted to say now that, and you should not you should not wrongly understand, or you should not misunderstand that 1 represents, means minus 1 represents px and plus 1 represents py and 0 represents pz. It is not like that. Okay, there are three quantum numbers, and corresponding to these three quantum numbers we can derive the expression for three orbitals px, py, and pz. And L is equal to 2. It means that d subshell. Okay, how many are possible in this one? M is equal to minus 2 to plus 2 through 0, means minus 2, minus 1, 0, plus 1, plus 2, plus 1, and plus 2. Okay, so 5 values are possible. It means that within D subshell there are 5 orbitals, right? Which are these 5 orbitals? You know these 5 orbitals. The d orbitals are d x z, d y z, d then x y, dx y, then dx square minus y square, and dz square. Okay, so 5 orbitals are possible there. So from this logic you can predict how many orbitals are possible in the F subshell. F is, for F subshell, L is equal to 3, and therefore there will be 2 into 3 plus 1, means 7 orbitals possible. So there are 7 F orbitals possible. Okay, so this is magnetic quantum number. And you know the shapes of these quantum numbers also. I am not going to the detail of that. And next, the quantum number is spin quantum number. Now you can consider that we've started from the principal quantum number. From the principal quantum number, we got an idea of the shell. From the azimuthal quantum number, we got an idea of the subshell, or subshells are residing within the shell. Okay, and from magnetic quantum number, we again went inside, means within the subshell we know which orbital. Okay, and now we know that each orbital is occupied by 2 electrons, and these 2 electrons have 2 spins. Okay, in order to represent that spin, we have a spin quantum number. Spin quantum number. The spin quantum number is represented by the letter S, and there are 2 spin quantum numbers possible for an electron, that is plus half and minus half. Okay, plus half and minus half. So one electron will have the spin plus half, and the next electron in the same orbital will have the spin minus half. Okay, so if we are specifying the spin also, then we can reach the electron within the orbital. So in order to get the address of an electron, we have to specify all these 4 quantum numbers. All these 4 quantum numbers. Okay, and one of the spin may be corresponding to the clockwise spin, and the other one corresponds to the anti-clockwise spin. Okay, so within the orbital, if one electron has the clockwise spin, the next electron should have the anti-clockwise spin. So if one electron have the spin quantum number plus half, the next electron should have the spin quantum number minus half. Okay, now I hope you got an idea of the quantum numbers, and there may be simple problems asked in the examination about the quantum numbers. So a question is, an atomic orbital has n is equal to 4. Atomic orbital has n is equal to 4. You can write down this question. An atomic orbital has n is equal to 4. So what are the possible values of L? So the question is, what are the possible values of L? The second question is that, this is question A. The second question is that an atomic orbital has L is equal to 3. What are the possible values of M? Okay, so atomic orbital has L is equal to 3, and what are the possible values of M? What are the possible values of M? This is the second question. And the third question is that, which shell would be the first to have an F subshell? Which shell is first? Which shell is the first to have an F subshell? F subshell. Okay, these are the questions. So n is equal to 4. What are the possible values of L? So you know, for n is equal to 4, the possible values of L are 0 to n minus 1. So that is 0, 1, 2, 3. 1, 2, and 3. These are the possible values of L. Okay, that answers the first question. The second question is that L is equal to 3, and what are the possible values of M? The possible values of M are minus L to plus L through 0, means minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Okay, these are the possible values of M. And the next question is that, which shell is the first to have an F subshell? Okay, which one is the first to have an F subshell? Which one is the first to have an F subshell? You know that S means there are many subshells, S, P, D, F. Out of that, S corresponds to L is equal to 0, P corresponds to L is equal to 1, and if D corresponds to L is equal to 2, and F corresponds to L is equal to 3, right? So which one should have this L is equal to 3? Where is L3 possible for the first time? Okay, if you are considering the first orbital, first shell, and L cannot be 3, because the only possibility is n is equal to 0, L is equal to 0. If you are going for n is equal to 2, then that is not possible, because the maximum value of L in that case is equal to 2 minus 1, that is equal to 1. And if you are going for n is equal to 3, the maximum value of L is equal to 2. Okay, so if L is equal to 3, then n should be at least 4, right? So if n is equal to 4, then the possible values of L are um, 0, 1, 2, and 3, right? And 3 corresponds to F subshell. So the last answer is which shell corresponds, which shell will have, which shell would be the first to have an F subshell? Which shell? That should be the fourth shell. Okay, the fourth shell is the shell which have fourth shell is the first to have an F subshell. And now we are going for another question. Which of the following orbitals are not possible? Which of the following orbitals are not possible? The options are 1p, then 2s, and 3f. Okay, so these are the options. Which of the following orbitals are not possible? You can actually say which one. Here one represents the principal quantum number. Okay, if you are seeing this kind of notations, here this 1 represents the principal quantum number. Here 2 represents the principal quantum number. 3 represents the principal quantum number. So if 1 is the principal quantum number, the only subshell possible is yes. So this is not an option. So this is not possible. This is not possible. 1p is not possible. What about 2s? Yes, it is possible because principal quantum number is 2. So the subshells possible are s and p. Therefore 2s is possible. Okay. And what about 3f? If 3 is the subshell, then only 3 subshells are possible, S, P, and D. So F is not possible. So these two are not possible. Okay. And then again there is a question. What are the N, L, and M values for 2px and 3p such orbitals? What are the N, L, and M values for 2px, then 3p z orbitals and 3p z orbitals? What are the N, L, and M values for 2px and 3p z orbitals? Okay, first let us go for 2px. In the case of 2px, principal quantum number is equal to n is equal to 2. And what about L? And L represents this one, P. And in that case, L is equal to 1, right? Because L is equal to 0 is for S, L is equal to 1 for P. And what about M? M represents the orbital. Okay, here it is 2px orbital. I already said if it is x, M is equal to minus 1 and plus 1. Okay, minus 1 and plus 1. There will be a combination of this minus 1 and plus 1 functions, and then we will get the 2px orbital. Okay. And what about 3pz orbital? 3pz orbital. In the case of 3pz orbital, n is equal to 3, right? And L is equal to 1 because it is p subshell. And now it is 3pz orbital. Since it is z, m is equal to 0. Okay, since it is z, m is equal to 0. And now we can go for the next question. Which of the following sets of quantum numbers are not permitted? Which are not permitted? Which are not permitted sets? We are given a sets of quantum numbers. We have to select which one is not permitted. The first set is n is equal to 2, n is equal to 2, l is equal to 2, m is equal to -1, and s is equal to plus half. Okay, this is first set. And the second set is n is equal to 3, n is equal to 3, l is equal to 2, l is equal to 2, m is equal to plus 1, and s is equal to 0. And the third set is n is equal to 3, l is equal to 2, okay, and m is equal to plus 2, and s is equal to minus half. And the fourth set is n is equal to 2, l is equal to 1, m is equal to plus 2, and s is equal to plus half. Okay, and which are the sets? Which sets are not possible? Okay, which of these sets are not possible? Let us examine each set. N is equal to 2, fine. L is equal to 2. If n is equal to 2, the maximum value of L should be 2 minus 1. So this is not possible. So obviously this set is not possible. Okay. And what about the next set? N is equal to 3 and L is equal to 2, that's fine. And m is equal to plus 1, that's also fine, because if L is equal to 2, m can have the values from -2 to +2, and s is equal to 0. Oh, that's a problem, because the possible values of s are plus half and minus half, so this is not a possible option. So let us strike out this. This is not a possible option. And what about the next? N is equal to 3, fine. L is equal to 2, that's also fine, because if L is equal to 3, the maximum value of n is equal to 2. And m is equal to plus 2, that's also fine, because m can have the values from -2 to +2. And what about s? S is equal to minus half, that is also a possible quantum number. So this is possible. And what about the next? N is equal to 2, fine. L is equal to 1, that's also fine, because the maximum value of L here is 2 minus 1, that's 1. And m is equal to plus 2. And which are the values possible for m? If L is equal to 1, minus 1 to plus 1. So m is equal to plus 2 is not possible. So this option is not possible. Okay. So from this one, the sets 1, 2 and 4 are not permitted. The only one possible set here is the third one. Okay. So let me give you some study problems, and you have to work out these study problems and upload in the classroom. Okay, in the Google Classroom. The first question is that assignment. The first question is, what are the n, l and m values? What are the n, l and m values of 3s and 3px electrons. 3px electrons. Okay, that's the first question. And the second question is, what designation is given to an orbital having n is equal to 3 and L is equal to 2 Okay, so so you have to answer this question, and here instead of orbital you can write given to a shell. Okay, so what designation is given to a shell? Given to a subshell. Having n is equal to 3 and L is equal to 2. Okay, so just upload the answers in the Google Classroom, and this will be posted in the Google Classroom. These questions will be posted in the Google Classroom. You just go and answer these questions. I hope you understood something about the quantum numbers. You can get more ideas just by reading other sources also. And if you have any doubt, don't hesitate to ask me. Thank you for watching, and stay tuned.